CADWOLF is a web-based mathematics and engineering platform. What that means is that first and foremost, it provides a place where any user can simultaneously solve and document any problem. For engineers, the platform is much more. This video introduces new users to the main components of the system and shows where each module fits into the solution process. A modern engineer or scientist uses a host of software platforms, word processors like PDF and Word, analysis tools like Excel and Numbers, programming languages like MATLAB and Python. Plus, there are issues with storing and communicating data. This causes problems. Documentation may not match analysis, managers or coworkers have licensing issues, and no one knows if what they're looking at is the most up-to-date version. CADWOLF solves these problems. It replaces word processors, analysis tools, and programming languages, and it introduces some functionalities not found anywhere else. The platform consists of 4 modules: workspaces, documents, datasets, and part trees. We'll go through each one independently, discuss their place in the platform, and look at some examples. We'll start with workspaces. A workspace is simply a web page that mimics the functionality of an everyday folder. This is where users store and create new items, as well as upload and store images. Your workspace is the default view in CADWOLF after you've logged on. All workspaces are accessed through a URL with the term workspaces at the beginning. To see an example, let's look at the workspace for the CADWOLF documentation. We're looking at this workspace through the eyes of someone who has permission to edit it. Each line represents a document, workspace, dataset, or part tree, and each column represents a property of that item or an action that can be taken on that item, such as moving or deleting it. New items are added to the workspace by clicking on the appropriate item in the menu. Adding a new workspace is equivalent to adding a subfolder, and you can navigate to it by clicking on the icon or by directly entering the URL, as we have done in the example workspace. This concludes our discussion of workspaces. Remember that they act just like a standard folder. Now let's move on to documents. A document is simply a web page that users add content to. This content can be text, images, equations, charts, and other items. Equations in the document are solved from top to bottom just like a program. They update automatically, track units, and have access to a wide variety of built-in functions like statistical tools and an FFT. All of this is done within your web browser with the phrase documents appearing at the beginning of the URL. Let's go through some examples to show just how powerful the platform is. This is one of our example documents that solves the roots of the quadratic equation. Along the left-hand side of the document is an edit bar where users can add new blocks, move a block, or alter the format of a block. This document contains a text block followed by 2 symbolic equations. Symbolic equations are simply formatted text and are not solved. They are used here to help explain what a quadratic equation is and the formula for its roots. After another text block, 3 equations were added and used to establish the values of the a, b, and c coefficients. Then, 2 more equations are created to solve for each root. Notice that we use the root and power built-in functions and that these functions display the results in the proper mathematical format. After some more text, we create 2 vectors that provide x and y data corresponding to the quadratic equation in question. Then, a chart was added and the x and y data set accordingly. When we change the value of one equation, say the a, b, or c coefficient, the equations in the chart that follow update themselves automatically. To get a better idea of what it looks like to build a document, we show the process sped up here. We first add a text block and then paste in some text. Next, we add 2 equations and then alter the default text to represent the desired equation. Finally, we add a chart, choose the chart type, add the x and y data, and change the color of the chart. Note that while this is done in order, you can add a new block anywhere on a document by simply clicking on an item and entering the desired block beneath it. Here's a basic engineering homework problem dealing with the loads on a cantilever beam. We have added some images, made use of the built-in integration algorithm, used some symbolic equations, and then solved for the final equations. Note that CADWOLF tracks the units throughout the entire document. In a more complicated problem, we solve for the position and velocity of a bungee jumper from the time of his jump forward. This makes use of numerous functions, including the differential equation solver in CADWOLF. We also have an example of the use of a Gaussian elimination algorithm to solve for the loads on a bar using the direct stiffness method. Now that you've seen some of the analysis capabilities of CADWOLF, let's look at some of the charting capabilities. You've seen some simple line charts so far, but CADWOLF has a full suite of charts available, including pie charts, bar and column charts, bubble charts, area charts, and heat maps. Additionally, any chart can be opened independently in a new window at full size. CADWOLF also has three-dimensional charts, such as the point cloud and surface maps you see here, as well as the ability to plot lines and use a number of predefined shapes. Every user can fully interact with the chart as long as they have a modern web browser. Here we see a path of a stunt plane through an obstacle course. The height of the line represents the altitude of the plane, and the color represents its velocity. The ground and obstacles are represented by predefined shapes. So you've seen that a document can contain text, equations, images, and charts. In addition to these things, users can also add video, tables that function like Excel spreadsheets, and programming structures like for loops, while loops, and if-else statements. A CADWOLF document can truly act as the sole platform to simultaneously solve and document almost any problem. Now that we've seen what a document can do, let's look at how to get data into a document. We've shown that workspaces are equivalent to folders and that documents are equivalent to files. Datasets provide a way to store data in a workspace and then pull that data into one or more documents. Datasets are simply web pages that parse text and store the results in variables. All datasets have a URL with the phrase datasets at the beginning. Opening an example dataset, you can see the four views. One to describe the dataset to readers, one to establish the method of parsing the text, one where the raw text is pasted, and one to view the results. Note the URL of the website, as this is how this pulls into documents. To pull a dataset into a document, the user simply opens the document, clicks on the dataset view, and then pastes in the URL of the desired dataset. A variable name is assigned for use within the document, and you can see the variable tensol is used throughout this document. Now that we've seen what a document can do and how to get data into it, let's take a look at what an engineer can do when he puts all of these things together. Workspaces, documents, and datasets combine to form a method of solving and documenting any mathematical problem. Part trees are a common engineering concept that CADWOLF adds a new dimension to. A part tree is a web page that lets the user establish a part numbering scheme, add parts to each system, and then view the properties of each part in real time. Each part is represented by a separate CADWOLF document where the design of that component takes place. This takes engineering from a multi-platform discipline with long redesign times to a single platform with automatic redesigns. Note again that every part tree has the phrase part trees at the beginning of its URL. A part numbering scheme is simply a way of tracking small parts of a large project. Every program has numerous systems which have numerous subsystems which in turn have numerous parts. Part trees assign a name to each part that indicates its location within the structure. For example, a part in a truck engine might have the number F150-engine-block-1035. The first three entries detail the vehicle in question, and then the system and subsystem in question. The last entry is a unique part number. Let's walk through an example to get a better idea of everything a part tree can do. The first view in the part tree module lets the user set up the part numbering scheme. The part numbering scheme you see here is a simplified version of a space vehicle system. There are 5 levels or blocks in the numbering scheme, and each level has a number of options. Looking at the part tree itself, you can see that under the Enterprise program, we have a capsule structure, a mechanisms group, and then a system called the DAS. This system is a series of struts that hold the weight of a docking system above a launch abort system. The 3 parts of the system are rod ends, fittings, and struts, and each part has a document associated with it that is accessible through the icon to the left of the name. The numbers to the left of the icons let us set how many of each item will be in the final system. It is in these documents that the design of each component takes place. Before we can complete this design, We need the design weight and the points where the system connects to the structure. Let's look at how part trees aid in the design and redesign of the system. Part trees do three things. First, they organize the parts of a system and the requirements. Note that the part number and the URL of the design document are identical. By creating a separate requirements document, we can read in parameters from both this document and the designs of surrounding parts. Second, it gives the user instantaneous feedback. We have a variable named weight in each document that houses the calculated weight of each part. The part tree lets us pull in that value from each document and see the summed results. This can be done with cost or any other metric. Finally, the part tree tells us when a design is out of date. The documents then redesign the parts based on the new requirements, and new measurements can be pulled and viewed immediately. Let's take a look at our example system and see how this works in real life. Here's our outside document that houses the requirements of the connection points and the design weight, which we have set at 15,000 pounds. Looking at the design of part 3, we can see that we are pulling in parameters from the requirements document as well as the designs of part 1 and 2. We use these parameters along with some material properties to calculate the length, thickness, and weight of the part. Back in the part tree, we pull the value for the variable weight, and it sums to roughly 112 newtons. This is one of the benefits of part trees, the instantaneous feedback of parameters. To see the other benefits of part trees, we change the design weight from 15,000 to 20,000 pounds. Looking at the part tree again, we see red indicator lights telling us that the designs are no longer valid. We then reload each design document, let them recalculate their values, and then save the results. We start with part 1, the rod end, because it is selected based only on the weight. We then reload the document for part 2, as it depends on both the design weight and the rod end properties. Finally, we reload part 3, the struts, as their design depends upon the weight, the connection points, and the properties of the two other parts. The part tree then shows that all of the items are now up to date, and you can see that as a result, the weight has now increased from 112 newtons to 138 newtons. What this means is that our entire system redesigned itself to adapt to the new requirement. This concludes the discussion of part trees. This example part tree, as well as the design documents, are available in the example folder. Let's move on to some of the other benefits of CADWOLF. CADWOLF offers a number of advantages over other systems. There is nothing to download or install, so there is no IT overhead. There are no issues with who is using what version of software. And since updates take effect whenever a page is loaded, your software is always up to date. You can also truly work from anywhere. Save a file at the office, use it in your lab, and edit it at home, all without the need to carry any files on memory sticks or use third-party storage. CADWOLF also has a unique permission system. A user can be allowed to only view a document, or they can be allowed to edit a document and save the changes. CADWOLF also offers the option to let a user use a document. This means that a user can edit specific equations and see the results of those changes, but they can't save their changes or edit every equation. This concludes our tutorial on the basics of CADWOLF. If you want to learn more, the site contains documentation, examples, and a number of videos like this one that teach the user everything there is to know about CADWOLF. To keep up with everything that's going on, follow us on Facebook.